call this moment a Big Bang.
Where we can't see shit.
Within a millionth of a second, the universe is transformed into a dense soup of subatomic particles. The expanding universe is now 3 minutes old, and energy is condensing, forming the building blocks of our modern universe. Electrons, neutrons, and protons. The universe is now 380,000 years old. The particles called electrons have slowed down and are beginning to be attracted to the protons. Each electron carries a negative charge, and each proton has a similar but positive charge. Their opposite charges balance each other perfectly, and they become the most important couple in the history of the universe. The first atom, hydrogen. Electrons are also caught by pairs of protons and neutrons, completing the second most simple atom, helium. The universe is now 500 million years old, and the hot energy soup has calmed down to a cold, dark cloud. A fine haze of atoms, mostly hydrogen, fills the universe. No galaxies, no stars, and no planets. Just atoms floating in space. And our story would end there, but for the invisible, inescapable effects of gravity.
Oh, what's a gravity?
Gravity is an invisible force that pulls in every direction from anything that has mass. Atoms are really, really small, but each one has a tiny amount of mass. So every atom's gravity is gently, almost imperceptibly pulling on every other atom in the universe. Slowly but surely, throughout the universe, gravity begins to shape the clouds of hydrogen. As more and more atoms are gathered together, they form into gigantic spinning clouds, the first proto-galaxies. As the galaxies take shape, bright spots appear deep inside. These new lights signal the birth of the first supermassive stars. Each star starts its life as a giant ball of cold spinning hydrogen. As the spinning cloud's gravity pulls in the surrounding gas, the ball begins to grow and grow. The more it grows, the more gravity it has, and the more it pulls in on itself. The atoms in the core are squeezed in tighter and tighter, raising their temperature to 10 million degrees Celsius. The heat and pressure force the nuclei of the hydrogen atoms together, and they release energy. As the energy escapes from its surface, the star begins to shine. If you could cut the star in half, you'd see outer layers of hot hydrogen plasma churning around a glowing core. The core is where almost all the heat is generated by a reaction called nuclear fusion. Nuclear fusion doesn't just make the star shine. Something new is being created deep inside. Ladies and gentlemen, for your entertainment, may I present a dramatic demonstration representing the wonders and secrets of nuclear fusion. Imagine we're in the core of the star. These balls represent the lone protons from hydrogen nuclei, and we're going to show you how they fuse together to form a new element called helium. The process starts with the protons. They're all trying to get away from each other because their positive charge forces them apart. However, sometimes a proton will lose its charge and transform into a neutron. Neutrons have no charge, so the heat and pressure forces them to join the closest proton. Together they become a new nucleus called a deuteron. The deuteron wanders around the core, but it is not long before it is hit by one of the free protons. The nucleus grows again. Then the nucleus tumbles around in the core until it meets another nucleus, and they are crushed together. 2 protons fly off back into the core, but the nucleus that remains now has 2 protons and 2 neutrons, the element helium. This process of fusing hydrogen protons is happening over a trillion times every second. Gradually, the helium fills the core. You might expect that once the core has turned all its hydrogen into helium, that it would stop working. But the element building has only just begun.
Welcome to the element factory!
As the hydrogen is used up, the core gets denser and hotter, allowing the helium nuclei to fuse into another heavier element, beryllium. Again, the temperature of the core rises and the beryllium begins to fuse with the helium into carbon. Fusing carbon raises the temperature of the core again. Under the pressure, the new elements start to fuse with each other and with the hydrogen. Many of the elements we know today are built in a star's core. Element we call iron is made. But the nucleus of iron is so stable that it can't fuse, and so temperature is no longer increased into the core. Suddenly, there is not enough pressure from inside the star to balance out the gravity pulling it in. Gravity wins, and the core of the star collapses. Slams the atoms against each other with such force, the star blows itself apart in a supernova. Supernovas complete the last stage in the element building process. Within these giant explosions, heavier, rarer elements are formed. Zinc, platinum, and gold. Over billions of years, the debris of exploded stars slowly collects together into giant clouds, still mostly hydrogen, but now peppered with a mix of heavier atoms. We call these giant clouds nebulae. This one is so big that it could contain our solar system hundreds of billions of times over. Deep inside these pillars, something is happening to the atoms. They are starting to reach out to each other and form molecules.
Excuse me, mister.
Yes, young lady.
What is a molecules?
Good question. Let's go take a close look. These are some molecules found in a nebula.
Ooh, molecules.
A molecule is a group of atoms linked up together like they're holding hands. You have this molecule in your body, and it's found in this nebula. It's water. A water molecule is made by one oxygen atom linking with two hydrogen atoms. You might recognize its chemical name, H2O. Another common molecule in a nebula is carbon dioxide, CO2, made with one carbon atom and two oxygen atoms. Your body produces carbon dioxide and you breathe it out. You all make this molecule too, except you don't breathe it out. Any ideas what it's called? Anyone?
What the f-
Thank you very much, but all I was after was the word methane.
You made a methane.
Right, moving on. When it comes to atoms in your body, carbon atoms are the most important. You see, carbon can bond with up to 4 different atoms at once, making it possible to create really interesting molecules. By linking it up with atoms like oxygen, hydrogen, and nitrogen, carbon easily makes some familiar molecules, like sugar molecules. It is in fat molecules and a vital part of protein molecules. Unfortunately, these molecules are quite fragile, and the radiation of space easily breaks their bonds. So we need to build somewhere that's protected and big enough to collect plenty of molecules. Somewhere like a planet. This giant disk of gases, molecules, metals, and dust is our solar system. And at its center is a very young sun. Within these churning clouds, gravity is pulling these molecules into great spinning masses that will become planets. This young planet is our Earth, already 1 billion years old. For over 100 million years, leftover dust and blocks of frozen gases relentlessly bombard the young planet. Each impact melting the surface and filling the atmosphere with molecules of carbon dioxide, methane, and ammonia. But eventually, impacts slow down and the surface begins to cool. The steam in the atmosphere turns to liquid and it begins to rain. It rains for thousands and thousands of years, eventually covering the whole Earth in water. Under this ocean, a new stage in the journey of atoms and molecules is beginning. water, heated by the molten rock of the Earth's mantle, bursts through vents in the Earth's crust, dissolving molecules along the way. As it meets the cool water of the ocean, these minerals are deposited, forming towers. As the molecular mixture passes through the mineral-rich chambers, they start to form the molecules we call the building blocks of life. Perhaps it was inside a vent like this, following hundreds of millions of years of chance interactions, that molecules formed the first life in the shape of cells. Under the ocean, these first cells used the molecules and atoms from their environment for energy and growth. It wasn't long before they began to make copies of themselves. Suddenly, there were hundreds, thousands, millions, trillions of cells spreading throughout the oceans. A billion years of random mutation resulted in a startling advance. Some cells began to use the sun's energy to turn carbon dioxide and water into sugar. This superpower, photosynthesis, let cells grow much more quickly. But a nasty surprise was in store. These new supercells released oxygen, and as this built up in the atmosphere, it changed our planet forever. Highly reactive, the oxygen poisoned a huge number of cells, causing a mass extinction. But some cells survived. As they replicated, they filled the world with cells able to tolerate or even use this new gas. And life sped on. Some cells began to work together and form groups until they had become the first multi-celled organisms. Over many generations, their forms slowly changed. Some of the original microscopic molecule factories had evolved into simple worms. It wasn't long before the worms evolved into primitive fish. Using iron in blood cells to capture oxygen and calcium to build bones, the fish continued to evolve and dominate the oceans. Over time, the molecules and atoms are constantly being recycled and modified as they pass from one living thing to another. Above the water, plants and giant insects took over the land. But they were soon followed by fish that had evolved the ability to crawl out of the sea and to breathe the oxygen-rich air. These oxygen breathers evolved into reptiles, which became the dinosaurs. And for over 100 million years, dinosaurs dominated the Earth, the masters of molecules, until... the giant impact changed the environment so rapidly that many forms of life were unable to survive. The age of the dinosaurs came to an end. But some species did survive. With the dinosaurs gone, mammals evolved to take their place as the new top atom organizers. Through the process of natural selection, they adapted to new habitats. As species died off and new ones flourished, a tree of life mapped out to the generations. Then millions of years later, on a distant branch of the family tree, there grew a new branch of mammals, the apes. Many generations later, on a twig from this branch, there stood some very strange apes. These apes were strange because their atoms had formed brains that didn't just think simple thoughts like, I'm hungry, but complex ones like, what are we made of and where did it all come from? They have been finding out the answers ever since. We have discovered that we are made of atoms, and these atoms are on a journey as old as the universe. Before they became part of you, they were in animals, plants, and in the air. They were once in dinosaurs, in primitive fish, and made up the very first cells. Cells assembled from molecules containing atoms that first arrived on Earth as comets and asteroids. Born within the clouds of giant nebulae containing complex atoms, delivered by exploding stars. atoms that have been fused by gravity deep in the core of the stars. Stars that were formed from giant clouds of hydrogen. The same hydrogen that was the first relationship between a proton and an electron. But it all started when energy came together to form matter after the universe expanded from a single tiny point. Roll up for the greatest show in the universe. We have gone on a journey to discover what we are made of and where it all came from. We have seen how the atoms in our bodies hold within them the history of the universe. Every atom, from the iron in our blood and the calcium in our bones to the oxygen we breathe, they all once came from a distant point of light. So, the next time when you look out at the night sky, remember where your atoms started their journey. We are all made from stars.